Things like bits can exist in the state 0, the state 1, but also in these states that are in between 0 and 1, which are called quantum superpositions of these two features. And that's simply not allowed by general relativity or by special relativity. This is the main reason, that's the fundamental reason why these two theories clash with each other. If you were to perform an experiment of the kind that I described, just you don't have the photon, but you have a neuron, for example, right? You put into superposition of being happy and sad, and then you rejoin the two states. What does that mean for that person? And this is very interesting, that things that don't happen have actually, that they actually have an explanatory power, and they are the reason why other things do occur, or at least can occur.
We have a sponsor for this episode of Apple Finch Pudding. But before I delve into this, I want to be very clear about what this sponsorship is being used for. This sponsorship is being used to support the podcast. This means paying for subscriptions we need, maybe some editing or some other material we need to make this podcast. That being said, our sponsor for this episode is SciSummary. As researchers, we need to read a lot of papers, and more are being published every day. As a result, reading papers is becoming more or less like a full-time job, leaving us virtually with no time to do our actual jobs, which is doing research. This is where SciSummary comes in. SciSummary provides you with an AI-based summary of the papers you provide. However, SciSummary is more than just a summarizing tool. It effectively lets you chat with your papers. You can ask questions like what materials and methods are being used, but it can even provide you with insights into potential avenues for future research based on the papers you provide. If you want, you can now try out SciSummary for 1 month for free. All you have to do is follow the link in the description below, or type in scisummary.com/AFP1 and use the coupon code AFP1. AFP stands for Apple Finch Pudding, 1 because you get 1 month of SciSummary for free. Try it out. If you like it, please go for it. If you don't, no hard feelings. But for now, let's go back to the show. Welcome to Apple Finch Pudding, your gateway into the world of science. Today's scientist is Chiara Marletto, a postdoctoral researcher in theoretical physics at Oxford University. Her work focuses on quantum theory. Chiara is also the author of the book The Science of Can and Can't. Welcome, Chiara.
Thank you. Thank you for having me. Yeah, great.
Before we start, do you have a fun science fact for our listeners?
If you have a problem that seems insoluble in a given framework, so for example, in physics, we've been using this approach that uses laws of motion and initial conditions to describe and explain the universe for quite a while, since Newton and Galileo. And lots of problems can be solved in that context. But if there is some problem that in that context seems to be problematic and not soluble, it's always possible to change the mode of explanation or the mode that you're using to approach this problem, and see whether in that different mode of explanation the problem becomes soluble, or sometimes it can dissolve. And so an example of this is, for instance, we know it's difficult to incorporate something like irreversibility in this framework of laws of motion, dynamical laws and initial conditions, because they are reversible. They have this property that they look the same when they go forward and backwards. Yet we do see reversibility at certain scales, and so it's been quite a challenge over the years, over the decades, for physicists to reconcile these two aspects. And I think if you change the mode of explanation, this problem can actually be addressed. So it's part of my research as just an example. But I think more generally, this is a kind of general fact that it's so easy to get accustomed to a given mode of explaining things because it works so well, that you may not even think of imagining a different way of explaining things and then trying to solve the problems that way, rather than sticking to the same framework and declaring some problems to just simply be not soluble. And so I think my research has been dealing with this thing a lot, and it's a beautiful fact about science. I would say this is more like a philosophical aspect of all of the sciences. You can always think outside of the framework that you've been taught within, and then imagine a different way of approaching a problem. So don't necessarily take the tools that have been working so well so far, don't take them for granted. And if there is something you can't solve with them, well, maybe it's time to try something new.
Yeah, no, and that's very interesting because I think when we're working on something, we get stuck in some kind of world and some paradigms we just accept, but
Yeah.
sometimes we just need to think out of the box.
Yes,
And
exactly.
I think you're alluring here to constructor theory, and we will get back to that a bit later, but
Yeah.
we'll build up to it. So you work in quantum physics, but could you very simply explain what quantum physics is?
So quantum physics is one of the two best ways we have to think about the universe at present. So it's a theory. It's a way of describing the universe, of explaining it, that's about 1 century old. So it was proposed about 1 century ago, together with general relativity, which is the other best explanation we have at present. And they were both proposed to improve on Newton's laws of gravitation and more generally Newton's laws of classical physics. Those laws were they became at some point unable to describe things like the stability of the atom and other phenomena to do with gravitation, also on the kind of cosmological scale, etc. And I think the effort of many great minds gave birth to these two theories. And quantum theory became a really important tool to describe specifically the microscopic scale initially. So that was the way it was approached initially. And I think the key idea, one of the key ideas at the start, was to understand that particles, things like electrons, neutrons, and so on, didn't have just the features of standard particles that we see at our scale, like a tennis ball. They actually behaved also like waves. So they were able to diffract. So if you shot some of these, if we were to shoot some of these particles against an appropriate grating with like holes that are kind of punched in a certain way, you won't see the typical distribution that you see if you were to shoot tennis balls, but you will see a distribution that's very similar to the pattern that you would see with a wave, like the sea wave or a sound wave. And it's counterintuitive because, of course, you're imagining these entities as very small entities like tennis balls. You imagine them as kind of miniature version of the tennis balls, but actually they are not. They behave in radically different ways. And this aspect that there is a duality between the wave behavior and the particle behavior was one of the initial slogans of the theory, in a way, the way to understand how quantum theory really works. It's been improved upon since then. And so this coming the second part of the explanation of quantum physics is around the 80s. This is getting closer to my own field of specific research, which is quantum information. So around the 80s, a bunch of people, including Feynman, and then some people like David Deutsch, who's a person that I've been working with here in Oxford, Jules, Charlie Bennett. This was an idea that kind of bloomed in many heads around the world at the time. But let's say, there was a bunch of people who started thinking that quantum physics could be useful, not just to explain, the microscopic world and tell us lots of things that allowed us to create new technologies like transistors and things like the diagnostic machines that we use for medicine and so on, but it could also be useful for computations. And specifically, the idea was that you could use quantum physics properties, the fact that particles behave both like waves and particles, if they are quantum mechanical, to power a different way of performing computations. So different algorithms that could exploit this wave aspect that is proper of quantum bodies. And the idea actually was fruitful. So around in the 80s, there was this proposal for a quantum Turing machine, a universal quantum Turing machine. And then some people thought of actual algorithms and quantum algorithms, and then quantum cryptography procedures that could improve on the classical versions that we already have. And so this gave birth to the quantum technologies, which are currently like almost a standard now, mainstream sort of engineering technology that's been developed around the world. But it also allowed us to understand quantum theory itself better. So trying to figure out how quantum systems can become vectors of information. So how can a bit become a qubit, so a quantum bit? What does it mean and what can it do? It led us to understand much better the foundations of quantum theory itself. And so I think quantum physics has given birth to this second aspect of the quantum revolution, which is the quantum information theory, which has now given us some very, very important theoretical tools that will be useful to imagine the next theory, because we know that quantum theory and general relativity work well in their domains, but they clash with each other. And so we expect that there should be a better theory that will come along at some point. Some people have been calling this quantum gravity. And I think the quantum information angle is very useful for that. So quantum theory is really like a set of very powerful theoretical conceptual tools that will survive its own demise, I think. Even when quantum theory itself won't work anymore, many of these ideas that power quantum information will still survive, in my view.
That was a lot of information, a lot of very interesting information. Maybe I'll start with, so you said that quantum mechanics and general relativity are like the two main theories or explanations, but you explained quantum theory, and could you also explain maybe very briefly general relativity and why they clash?
So general relativity is the natural continuation of the thoughts that Newton had about gravitation. Gravity was understood as a force in Newton's setting, whereas Einstein's intuition was to explain it through a different set of properties which have to do with geometry of space-time. And through Einstein's intuitions, we managed to understand that, for example, time intervals and distances are not absolute, but they actually are relative. So they're not invariant when you change frame of references and so on. And through this, we managed to explain phenomena that Newton's laws couldn't explain by themselves. And the fact is that general relativity is radical in the sense that it really changes lots of features that Newton's laws had. However, if you look at let's say, the information theory structure of these two theories, the classical laws of physics that Newton formalized in his laws and general relativity's laws, you will see that even special relativity's laws, you will see that they are all classical from the point of view of information theory. So if you were to discretize these laws and sort of wanted to describe them in a computational analog way, you would use bits, just classical bits, things that can be either 0 or 1 at one time. But as I said earlier, quantum physics has this other take on things and says that things like bits can exist in the state 0, the state 1, but also in these states that are in between 0 and 1, which are called quantum superpositions of these two features. And that's simply not allowed by general relativity or by special relativity. This is the main reason, that's the fundamental reason why these two theories clash with each other. There are different proposals to put them together. It's easier to put them together when you consider what specialists call the low energy regime. So when particles are going relatively slow compared to the speed of light, so they have low energies. But unfortunately, these schemes require a number of approximations and they are not satisfactory. So they may work well for some special regimes, but they are not the ultimate theory that will merge the two. And people are still looking for the right candidate. There are some candidates that haven't been tested yet. And so we have a big question mark on our heads in terms of what will be the next theory.
This combination of classical and quantum physics actually brings me to one of your papers. The title of the paper is Temporal Witnesses of Non-Classicality in a Macroscopic Biological System. That's a recent paper of yours.
Yes.
So this suggests something quantum mechanic, or at least non-classical in a classical system. I think it was here in photosynthesis. Could you explain what that means exactly?
Yes. So that work, which, by the way, this is some work I've done in collaboration with a DPhil student in Oxford, who's called Giuseppe Di Pietra. And in fact, he's the person who kind of brought forward the work most. I mean, I kind of was helping him in a sense. So this is really his thesis work. But it was very interesting to me because it was an application of a number of other things that we developed in the past. And the problem there was we were trying to understand a situation where usually people think that quantum theory may break down. So there is in the physics community, there's a camp of people who's been thinking this kind of dates back to the founding fathers, back to the, people like Wigner, Bohr, people like that. They thought that quantum theory may have to break down at some point, because after all, when, at our scale, we don't see these effects. As I said earlier, back to tennis balls, if you think of a tennis ball, it doesn't behave like a wave, and that's because we are at the wrong scale in a sense. So the idea was that not just that natural occurring macroscopic objects don't display naturally quantum effects, but it's really that even if you were to perform a very complicated experiment, you would not be able to elicit any quantum effect in a macroscopic object. So these are two different statements. One is to say, well, we can't see quantum effects naturally. However, if we throw enough resources, throw enough money at an experiment, you will eventually be able to put a tennis ball in a quantum superposition. It just requires a lot of effort. Whereas the other statement is no, these quantum effects are just impossible to create in objects that are above a certain threshold in terms of mass or size, more generally speaking. And so biological objects have traditionally been an instance of objects that are large enough to already create some problems with quantum physics. So people who expect quantum physics to break down at some scale would say already that something that's as big as a cell, for example, I don't know, a human cell, has a mass that's large enough to already create some issues with quantum theory. And, there are theories like Penrose's collapse theory that's predicting exactly a collapse of the wave function. So these quantum superpositions should disappear beyond a certain scale. And so the paper in question addresses this issue and says, well, suppose you want to test these two views, that a mesoscopic biological molecule, which could be a polymer inside a bacterium, or it could be a cell, as I said, that's photosynthetic. It depends on the setting, but it doesn't matter. It's a very general argument. Suppose you want to test the theory that this object does have some quantum features, after all. How do we do that? And in the paper in question, we were thinking of, instead of measuring directly this entity that we want to test, which is what you would normally do, we were thinking of coupling it with another system that we know it's quantum mechanical, such as, for example, a photon. A photon is a quantum particle of light, and in the laboratory, it's very easy to manipulate them, relatively easy to manipulate them in a quantum mechanical way because we already had the technology. So we couple this photon with, for example, a photosynthetic molecule inside a living system. And then by appropriately tuning the interaction, we see whether this molecule is capable of inducing some dynamical evolution on the photon. And then we measure the photon again. And if the photon has evolved in some way that has quantum mechanical features, by the argument we explain in that paper, this becomes like a witness of the fact that the molecule itself, which was in question to begin with, has quantum effects in itself. So it's non-classical, or it's quantum mechanical. And to do this sort of reasoning, you need to make a number of non-trivial theoretical steps. But the power of the argument is really that it allows you to infer something about these objects that are macroscopic or mesoscopic that usually are very difficult to experiment on directly, by coupling it to something else, like a photon, that's instead easier to address experimentally. And so by looking at what the photon or the quantum probe more generally does, you can infer properties of this other mysterious or problematic object whose quantumness you're questioning. So I think that's the gist of the work. And it's part of a general set of works that we've been kind of studying for a while, where we are trying to study these systems where you can have a situation where a quantum object, which really behaves quantum mechanically, interacts with something that the skeptic would say may not be quantum mechanical. And we're trying to provide witnesses that allow you to test in the lab that, after all, the other object is quantum mechanical. So if you haven't guessed it already, if you think of the two camps, the one that says quantum mechanics is universal, the other camp says, no, it's not. I belong to the universality camp. So I'm very much in favor of the fact that quantum theory does apply, to everything in the universe. It's just that we We don't see it at our scale simply because it's not easy to see these effects. But if you were to invest enough knowledge and resources into an experiment, you would be able to put any object in a quantum superposition. It's just a question of time. We have to wait for someone to have a brilliant idea about how to do it.
And yeah, so this also brings us a bit to out of the box thinking that you were talking about before. And so yeah, I want to allude a bit to constructor theory, but I have tried to understand it. And so I'll say what I think it is, and then you can correct me. So in quantum mechanics and classical mechanics, we have a system and we start with boundary conditions and we go forward or even backwards. And that's how everything is happening. In constructor theory, you just say, give me a complete set of everything that is possible and also what is impossible. So factuals and counterfactuals, and within the laws of physics, of course. And based on this information, I can carve away and get the laws of physics out of that, or at least get more information on what is happening in the universe. Is that correct?
Yes, I think broadly speaking, I think this is what this does. I need to perhaps give a bit more context to understand, for example, the name, why it's called constructor theory, and maybe a few examples will clarify a bit better how this works. But you got it right that the main idea is to really switch from from the standard approach, which is to take these microscopic dynamical laws as the fundamental things with initial conditions or boundary conditions, as you put it rightly, and instead consider these general statements about which transformations are allowed or disallowed, possible or impossible to be more precise, as the fundamental statements, and then the dynamical laws are somehow a consequence or explained by these principles. And the name constructor comes from a term that was introduced by John von Neumann in the 50s or 60s. So John von Neumann had an idea to generalize the Turing machine. So he was interested in computational biology, so he wanted to understand biological systems through computation.
Sorry, could you also explain the Turing machine in this story?
Yes, that's right. So the Turing machine is a model that was proposed by Turing to capture all computers. So any computer that we are using is in fact an instance, a practical instance, and kind of a real instance of this model machine that Turing invented. And so it's a device that can get an input, some instructions, and perform a computation on a tape. It's got some infinite amount of tape to work with and unbound it, and then it can erase things and write on the tape, and that's all it does. And Turing proved a number of properties of these Turing machines, what are their limits. And then the scheme was extended to quantum laws, and turned out that they can perform the same computational tasks, but the quantum Turing machine can perform more general class of algorithms, precisely because it's using quantum bits. And von Neumann then, actually this happened before the quantum Turing machine, von Neumann wanted to use the Turing machine, the model in a computer, a programmable computer, to emulate life. So the fact that living systems can self-reproduce, this was something that von Neumann wanted to understand computationally. And he realized that if you try to program a computer to create a replica of itself, you just can't. It's impossible to do that. You can, of course, simulate in the workspace of the computer a living system that's self-reproducing. That's one thing that you can do. But if you really want your computer to build a replica of itself with raw materials, there's no space for that. And it's not because your computer is not well built. It's simply because the Turing machine, the universal Turing machine model, doesn't have that concept in it. It doesn't have the arms to do the work. It doesn't have the space. So it's just not designed to perform that kind of task. So then von Neumann thought, okay, let's define a more general kind of machine, and I call them constructors. They're not just computers, but they're machines that can be programmed to perform physical transformations that are more general than just computations. So they do contain a computer usually in them, so they can be programmed. But this computer is controlling a number of other things, arms that can assemble things together, and various other tools that are needed to perform more general transformations. And the thing that he conjectured was that just like there is a universal Turing machine, which is the most universal computer you can think of, there should also be a universal constructor. So a programmable constructor, a programmable machine that can be programmed to perform all tasks that are physically permitted, that are physically possible. That's where the name constructor theory comes from, because if you think about it, a machine of this kind, which you can think of like as a universal 3D printer that can create anything you want within the boundaries of the laws of physics, given raw materials, this machine should be bound only by the laws of physics. So what it can do, it's exactly the set of possible tasks that are allowed under a given set of laws. And what it cannot do is just a set of impossible tasks. So constructor theory is called like this because the hope is that by understanding all the tasks that are possible and those that are impossible and formulating laws of physics this way, you are indirectly describing also the repertoire of the set of capabilities of this universal constructor machine, assuming that it's possible in our universe. And this also tells you indirectly that we don't have a theory of these machines yet. So von Neumann conjectured the idea of a universal constructor, but then he didn't develop the theory of these machines in real life. So he studied them within the Serre automata type framework, which is a very computational model that is very abstract and is distant from the actual laws of physics. And so there isn't an actual theory of the universal constructor the same way that we have a theory of the universal computer. And so when David Deutsch, who is, by the way, the person who proposed constructor theory when I was a student here as a kind of PhD student, that's how I stumbled upon the whole thing. He proposed a theory, and he was hoping this would also become the foundations for this theory of the universal constructor. Not only that, but also they would generalize the theory of the universal quantum computer to cover these more general machines. That's why it's called constructor theory. And the reason why I got very excited about it is that, okay, at the time I was interested in quantum biology and I wanted to understand self-reproduction of cells within the idea of a constructor. So somehow stumbling upon constructor theory was very useful. But then I realized that constructor theory was much more general than just that. And I found it very promising because it's formulated in a way that's not rooted into any specific dynamical theory. So it doesn't use the equations of quantum theory or general relativity or Newton's laws. It's more general and it's formulated at the level of these principles. They're a bit like thermodynamics laws, the conservation of energy, or things of that kind. And this allows you to use them in situations where you are not sure which dynamical law you should use. So going back to what I said earlier, for example, when you're studying where is it a quantum theory breaks down, you are not sure if you can use quantum theory's laws because you don't know if they apply or not in a given context. And so having principles like constructor theories that still apply in these kind of domains is very useful because you can still make predictions, you can still explain some phenomena, and you can still make some testable statements about a given system. And in fact, most of these witnesses that I mentioned earlier, which actually lead to actual, to testable predictions, have been formulated through principles of constructor theory, which is a very useful thing. Besides, because you're not rooted and you're not constrained within a specific dynamical law, you can also use these principles to conjecture new laws. So for instance, if you're looking for the successful quantum theory, having these principles laid out is very useful again because they can be a bridge to guess this new dynamical law. And ultimately, this is something that we haven't fulfilled yet. So this constructor theory is a little like a program, and I've been working on aspects of it, but it hasn't really been completed. The hope is also that it could help us understand things like the dynamical laws and initial conditions better. And again, the fact that you're switching from one mode of explanation to another, and this has been true time and again in my work, allows you to solve some issues that have been long unsolved in the dynamical law type picture. And that's what we're doing basically with this program.
Is it correct? Like in my head, I see some kind of black box of everything that is possible. And then you put your limitations and you carve out pieces of the box. And afterwards you can see what is still connected and what isn't. Is that a way to visualize it?
Yes, it's very useful to have this sort of mental image, I think. And another aspect is that once you do that, you can also show that the possibility of certain transformations, for example, the fact that you can have entangled particles in a given system, follows directly from the possibility or impossibility of other transformations that are more primitive. And this is how the explanation works. This is the explanatory power of constructor theory. So, for example, we have some principles that we formulated with David about, some principles that rule physical systems that can contain information. And these principles are very intuitive. So, for example, the fact that you can copy information from one support to another, this requires the possibility of certain tasks. And this itself, plus a number of other constraints, allows you to explain things like the properties of quantum systems. That's very counterintuitive, but it is how it pans out if you look at the problem through constructor theory. So I think the explanatory power is to use the principles to explain unexpected consequences of something that appears to be simple and intuitive, such as the copyability of information.
I don't know, but in my head, I see a strong connection like with how AI works, because it's also like you put some data in and you know what comes out. You don't know the connection, and AI is like looking for the best connection, but we don't really know what is happening. Is that something similar then?
I think the logic it's a nice analogy. I hadn't thought of it like this before, but I think somehow there is some analogy there. So we always conjecture these principles as, well, to capture some regularities that we see in nature. And then out of those principles, you use some logic to infer consequences that are unexpected. This is true of all physics. But in this case, because you're talking about tasks, there is maybe a stronger analogy with what you were saying. And there are some cases where this is really unexpected. Another good analogy is also with thermodynamics. I think thermodynamics has been used for many years exactly in this way. So, for example, you have the second law that says that, I don't know, you can't convert heat into work with no other side effects, because otherwise you would violate the second law. And I think this type of constraint allows you then to explain why, for example, a heat engine has a certain efficiency in a given context. Why is it you can't exceed certain power in another context, and so on. And this is our consequence of this very, very simple statement that really forbids some transformations from being possible. And it's quite powerful. If you think about it, actually, there are lots of this mode of explanation has been used within physics already a lot. It's just that it hasn't been done in a systematic way. And I think constructor theory is trying to do that systematically and extend it to other areas, not just thermodynamics, but other areas of physics too. And then use this to also bridge the gap between physics and, for example, the study of properties of life, and maybe the mind as well, as you mentioned.
And is the end goal of constructor theory then to find new laws, or is it a theory on its own?
So constructor theory is a meta theory, if like, or a higher level theory, a bit like thermodynamics. So it's designed to constrain a number of possible dynamical laws, and its principles should be suitable to explain a bunch of different dynamical laws, not just one. So it won't single out a single dynamical law. So it will be useful also to trim down the number of candidates for, say, quantum gravity, for example, or whatever other theory you may be thinking about could be the successful quantum theory. And this is the role of principles in physics in general, that they're useful as bridges to imagine future theories of physics. And they have also this feature that they're quite robust if you get the right formulation. Like the second law, right? It's survived many, many years, and it's very difficult to shake. Conservation of energy is similar. Principle of locality, it's also similar. They hit on a regularity that's very robust, and it's true of many, many different dynamical laws, even when we change them as we go along and we discover that one doesn't work, like in the case of Newton's laws.
And this framework is based strongly also on counterfactuals. What are counterfactuals, and can you give some explanation or some examples?
Yeah, this is very much in the philosophical realm, and I think I often explain that the way I mean counterfactual is perhaps different from what most philosophers would imagine. So the way we think of counterfactual is simply to think of statements that are not about the actual. So when you look at the dynamical law and the way it unfolds given an initial condition, it just says a sequence of things that occur one after the other. So these are factual statements, or they're kind of, like a sequence of things that are actually occurring or that will occur, that have occurred. But when you say that a given transformation is impossible, for example, if you say it's impossible to convert all heat into work, or it's impossible to copy a set of states, so from a quantum system to another, you're not referring to anything that's happening. In fact, it's an impossible thing. But it's still a statement about reality. It says that something can't occur. And it's very useful to explain why other things can occur. So, for example, why is it that the heat engine ultimately has a given power once you set it up in a given way? And in the case of what I said about copying quantum states, why is it that you can create entanglement in a given system? Because that's a direct consequence of the fact you can't copy certain states of the quantum systems. And this is very interesting, that things that don't happen have actually, that they actually have an explanatory power, and they are the reason why other things do occur, or at least can occur. And even when you say it's possible that something happens, that's another counterfactual. It's not an actual state. You're not saying that something is going to happen, or has happened, or is happening. But the possibility is something that can have an effect. A good example for maybe a non-specialist is to think of stock market, or, if you say something is possible that a given event could occur, that's enough for some people to sell a lot or to buy a lot, and this has real consequences. So the counterfactual fact that something could occur can have real consequences, and can explain also why certain things occur in the stock market. And likewise, more generally in physics, when you say, for example, that energy is conserved, you implicitly say that some transformations are allowed, which are the transformations that conserve energy, so that you transfer energy from A to B. And that itself explains why some systems behave the way they do. For example, why is it that there can be some frictionless dynamical systems, and why is it that they, you can set up initial conditions and run the dynamical laws, and if they conserve energy, they have a certain set of features that unfold under your eyes. So somehow the possibility of something that may not actually occur is used to explain, again, something that you see occurring before your eyes. And this is a general thing in sciences, I would say, in general, right? So in biology, to understand how genes work and how the gene expression works, you have to think of what could have happened if you hadn't had that particular gene being expressed, and so on. So the counterfactual reasoning is ubiquitous in science in general. But we're trying to make it become almost like a paradigm in this framework by using statements about possible and impossible tasks to explain the actual, so that, what we observe in the lab ultimately.
It's really interesting because I have never thought about the idea that something being impossible actually gives information about what is possible.
Yeah, that is very
Yeah,
interesting. I agree. It's
yeah.
it's it's counterintuitive, but it's really useful to. The impossibility of something actually explains why certain things are possible. Yeah, that's very interesting. That's true.
It might be a bit of a stretch, but from the idea of counterfactuals, could you describe the many worlds theory or quantum multiverse as an interpretation of quantum mechanics where all possibilities occur in separate branches of the universe? Is that correct?
I think this makes sense. There is one thing that has to be clarified, which is that some people have in mind the fact that many worlds says that all logically conceivable things occur in some of the branches of the wave function. This isn't the case, so that we have to distinguish a little bit, in the sense that according to many worlds interpretation, it's true that the universe has a wave function, so it's described by some quantum state, which is a superposition of different possibilities. However, each of these possibilities still obey the principles of physics as they are. So, for example, there shouldn't be a branch where conservation of energy isn't satisfied, or say where the second law is violated. And so each of these branches will still have the properties that we expect are exactly true of the universe. It's just that they will have different other things occurring. And there is a different kind of multiverse that some people talk about in cosmology, for example, where you do consider universes which may actually violate some of these principles. But this is a different kind of notion of multiverse. The quantum multiverse is really whatever thing comes along with this quantum state of the universe, where not just the thing that we do see in our own universe occurs, but also other possibilities occur, just that they are some other, we can't communicate with these other universes. We cannot perform an experiment that interferes these universes together simply because they've been crystallized in this way. However, if in principle, if you talk about a subsystem of the universe which is small enough and you have enough control over it through, for example, a laboratory, the quantum alternatives that the wave function describes can be interfered together. So, for example, when you do an experiment on a photon and the photon is set into a superposition of two paths, here or there, an interferometer is a standard way of rejoining these two possibilities into one. So you can do an experiment with the photon where the photon goes through a crystal that splits its path, and then the photon goes onto each of the two paths and then can be remerged with the same crystal into one path, single path. This is an interferometer, and this is the way in which you kind of can merge two universes into one. This happens when you have control on the object. The larger the object, the more interaction it has with the universe, with the rest of the universe, the harder it is to perform this rejoining of the possible branches. And in the case of the universe, or even in the case of a microscopic object like a person, for example, it's just very difficult to imagine an interference experiment being performed on this entity simply because it's too complex. However, we go back to what I was saying earlier. Those people who believe the quantum theory applies universally would have to admit that if you were to work hard enough, you should be able to perform an experiment, even on something as complex as a brain, which leads to a number of interesting possibilities in the sense that there are lots of experiments that, to begin with Schrödinger's cat experiment, but also other thought experiments that people have been thinking about, where you can imagine what would occur on, in a person's brain if you were to perform an experiment of the kind that I described. Just you don't have the photon, but you have a neuron, for example, right? You put into superposition of being happy and sad, and then you rejoin the two states. What does that mean for that person? And there are a number of answers. We can discuss it. People have been thinking about it a lot. There's even an experiment, David Deutsch proposed one such experiment a while ago. These are all thought experiments. Obviously, no one has performed anything like that. But we're getting closer to being able to at least imagine situations where you can have a neuron or this part of the brain coupled with a quantum particle and see whether you can keep some, you could start thinking what would happen if you could keep some coherence in that interaction. And these are all naturally building steps for performing experiment of the kind that I said. And as I said, if you expect the quantum theory applies to everything, it's very difficult not to think in terms of many worlds. Or at least you have to acknowledge that these branches of the superposition, of a quantum superposition, do exist. And then if you don't want to say that the mind is something that you cannot describe with physics, which is something that most physicists would not want to say. So we all expect that the mind is made of, of atoms, and we describe it within standard physics. Then you would have to either say quantum theory is wrong and therefore it doesn't apply to the mind, so we need a different theory. Or if you say quantum theory is the right description, ultimately you will have to admit that the mind has to exist in quantum superpositions. I don't think there is much room to maneuver there. So I think I belong to this latter camp. I'm very happy to imagine these states of mind, and it seems to me it's reasonable to expect that that's the case.
One thing from the beginning, it already piqued my interest, was also you have two different types of multiverse. So the one from cosmology and the one from quantum theory. So it almost feels like there's a multiverse of multiverses. I mean,
yeah, I think so. I think the cosmological multiverse is more like a conceptual tool that people use in order to understand things like the fine-tuning problem and stuff like that. Whereas the actual quantum multiverse is a thing that that people use to describe what the universe looks like if you think of it in terms of the many world interpretation, which, to be fair, really, I think the many world interpretation has been interpreted too much. So I think somehow, first of all, if you talk to a person who says I'm a person who thinks the many world interpretation is true, and then you pick another person that says the same, you will see that they have different views about what it means. So that's one problem. And also, lots of terms have been overused. For example, a world is often, people think of it as something overly complicated. Whereas, as I said, it's already enough if you have a photon that's superposed across two different locations. That's already a situation where you do have two branches, if you like. You don't have to use the word name world. But there are these two branches where the photon is doing different things. And quantum theory says they coexist and they are both there. And then, there's a question of how come when you observe the photon, you only see one and not two? And the reason is simply that quantum theory says that you can't observe both. You would violate the basic principles of quantum theory. You would violate the Heisenberg uncertainty principle if you were to do that. So you have to admit that there are things that exist, but you can't observe directly. That's the thing that most physicists who don't like quantum theory, including Einstein actually, and many, many others who were extremely perceptive and actually invented the theory themselves, but they didn't like it. The reason why they didn't like it is because there is this aspect that you have to, you have to let go of this control thing that you can't, there are things that the theory says there are things that you cannot directly measure, but they are there. You can measure them indirectly. It's not that they are untestable. So the fact that the photon is in both branches has testable effects that you can test. So it's not that it's some sort of unicorn-like scenario. But the fact is that you cannot directly see these things in the same way that, I can see that this cup is white and has a fox on it. It's just so this is a very deep philosophical issue. It also goes back to empiricism, the fact that people who think, some people expect that all aspects of the physical theory should be directly observable, observable in a laboratory, for example. That's not necessarily true. Of course, you have to be able to test a theory that there must be predictions, otherwise it's not physics. But it's okay to appeal to some entities that are mathematically expressible, such as, for example, operators or matrices or whatever. And even if you can't observe them, you can still say that they represent some properties of a physical system. And so I think ultimately what quantum theory says is that you can call it the quantum multiverse, or you can call it Q numbers if you talk about these properties of objects being matrices and not numbers, not real numbers. You can use lots of different ways of talking about these things, but ultimately what it says is that there are some features of a physical system that cannot be all directly observed in a single experiment. And that's very different from what classical physics says about the universe, because classical physics, including general relativity and special relativity, all of these theories and Newton's laws say that if you take an object and you have a powerful enough measuring device, you can measure all the properties at once. Its velocity, its position, its color, its shape, all of these properties are measurable all by the same device. So if you had a way to augment your eyes, your senses with this hypothetical device, you would be able to perceive all of these things together. And quantum theory says it's not the case for quantum systems. If you can see the position, you can't see the momentum or the velocity. That's for electrons. And for a spin, you can see if you can know the orientation along one axis of a spin, you can know it along a different axis, and so on. And that's the fundamental reason why people are uneasy with this. And the many welders usually they are happy with this fact, and they're happy to let go of the fact that there are these things that you can't really directly observe in a single shot experiment. But they are happy with the fact that these things actually do have experimentally relevant consequences. And they use these things to explain what we see in the lab, ultimately.
you can show with experiments that many worlds theory exists or is happening?
Well, this is a tricky question because I think I would say yes, but I think the problem is that all of the unless we're talking about collapse theories like what Penrose is and Yoshi, so there are lots of theoreticians who would proposed ways to modify quantum theory to account for something that they call the quantum state reduction, so the fact that the superposition of different possibilities collapses into one or the other. But if you don't discuss those variants of quantum theory where you really have a different equation of motion, if you just talk about interpretations, they are designed to agree on describing what we see in the laboratory. And some of them are a bit shifty about where is it quantum theory would stop applying. So for example, there are some people who are happy with the fact that quantum theory applies to whatever your instrument is experimenting on, but then they want to have a classical realm outside. And they are not clear about how that comes about, why it is there, what happens if you hit the boundary of the universe, where is the classical realm. So all of these things are a bit, often are left unexplained. But if you simply talk about interpretations, it's very difficult to discriminate one interpretation against another simply because they're all designed to agree on the actual outcomes. However, if you insist on some philosophical soundness of what you're saying, that's what I would say, kind of saying it in a very open way. And if you insist on some reasonable other principles, for example, you want locality to be true, you want, so locality meaning no signaling, you want a continuity of description, so you're not happy with saying, okay, I apply my theory up to here, not beyond, and I don't mind where here is, I don't want to say where it is. So if you're not happy with any of these fudges, I'm afraid you will end up having to land on the many worlds picture, which is actually just quantum theory. That's what I was saying earlier, that there is no escape if you take it seriously. If you take quantum theory seriously, it's kind of a phrase that David likes a lot. And I think Wheeler also liked it. If you take quantum theory seriously, then you end up, you have to think the many worlds way. It's very, very difficult not to do it. If you don't want to do it, then you have to create a contrived, it's a bit like the epicycle with trying to explain the movements of stars without thinking that the Earth is kind of orbiting around the sun and not vice versa. So if you start thinking the Earth is the center of the universe, you will have lots of problems. You may be able to explain something, but then you end up with a theory that's very contrived. And that's the same way I feel about the other ways of thinking about quantum theory. If you try to deny some of these other aspects of quantum theory, then yeah, you may still be able to explain what we see in the laboratory, but it sounds very stretched. And so, yeah, so I think I'm happy with taking quantum theory seriously. They applies everywhere. And then consequences, you just wrap a towel around your head and then you go with it.
Okay. Before we close, do you have a take-home message for our listeners?
Yes, I think we discussed lots of things. And I think, if this is a thing that's heard by people who are doing research or they're interested in science or some in creative work, I think one aspect one thing I've learned through my work is that it's really important if you decide to do this kind of work that you try to follow what you really like. If I had one thing to, one message that would be nice if you kind of brought it home with you, is the fact that it's really important to follow what makes you have fun when you're doing research. And I think this thing of seeking interesting problems, interesting to you as a researcher, is a thing that is often neglected. It seems to me that there's a lot of pressure, especially on not just young researchers, but also mid-career researcher, also all the researchers who are at the end of the career. I think everyone is somehow encouraged to maybe follow fashions or try to do things that are profitable for a given grant to get more money for support and so on. And yes, it's true that we all have to sort of find something to live on, and etc. But within reason, it would be nice to try to put a stop to these tendencies and really do the research that makes you happy and interested. Because if you're doing something that's only half-heartedly interesting to you, it's unlikely that you will, first of all, you won't have fun. And then also it's very difficult to really try to squeeze everything out of the problem in question. Whereas if you really do something that you're interested in, you will be able to extract the best out of yourself and the problem, and then most likely you will solve it or make a nice contribution to whatever thing you're studying. So yeah, I think follow the delight in pursuing knowledge, and have fun with whatever you're doing.
Thank you. That is a great sentiment.
Yeah, I think it's important. People don't say it enough, and I'm hoping I would like more supervisors to remind this, remind the students about this, because it's really important, I think.
I totally agree. This was Apple Finch Pudding. I want to thank Chiara Marletto for the information. Let's meet again for the next episode of Apple Finch Pudding.